All right, draw a mapping diagram of the ordered pair shown. So our mapping diagram is made up of two ovals. One oval is going to have my x coordinates in it, and the other oval is going to have my y coordinates. So my x's are 3, 5, 7, 11, 13. My y coordinates 17, 19, 19 again, we only list it once, 23, 29. Then I draw arrows to represent how they're related. So 3 goes to 17, 5 goes to 19, 7 goes to 19, 11 goes to 23, and 13 goes to 29. All right, which gives us C. Now, the second part of this question says, is this a function? Well, to be a function, all right, you can't have an x cannot be mapped to two different y values. All right, so if you had two arrows coming out of an x, then that is not a function. All right, so we don't have that case here. So this is a function. And then there's two types of function. There's one-to-one, and then there's a many-to-one. Okay, our example is many-to-one because 3 and 8 are both paired with 7. So that's where you get many-to-one. That's still a function. All right, for the linear function f of x equals mx plus b, we're told that f of -6 equals 16 and f of 9 equals -14. And then the question says find m and b. All right, well, what function notation means? This here tells us that an x of 6 gives you a y value of 16. And this one tells you that an x value of 9 gives a y value of -14. Okay, now this is the equation. This is a linear equation here. And m is the slope. So our slope equation is y2 minus y1 over x2 minus x1. The b represents the y-intercept. So I'm going to do my slope first. So I'm just going to call, let's say this one x2, or excuse me, y2, x2, and this one x1, y1. So I will have -14 minus 16 divided by 9 minus -6. So that gives me -30 over 15. So when I simplify that, I'm going to get -2. All right, so now I know my m, my slope is -2. So I'm going to take out m and replace it with -2. Okay, and now I want to find b. So remember, f of x, guys, is the same thing as the coordinate y. So I'm going to take that out and replace it with a y. And now what I'm going to do is I'm going to substitute one of the coordinates of one of these points. So I can substitute -6, 16 or 9, -14. It doesn't matter. I'm going to use -6, 16. Okay, so negative 16 is my y, negative 6 is my x. So this would become 16 equals negative 2 times negative 6. And now I can solve this for b. So my m value was negative 2 and my b value was 4. Okay, find the domain and the range of this function. So our domain refers to all the possible x coordinates. Okay, so looking at our drawing here, the smallest x coordinate, and we go from left to right here, would be negative 4, and it's included in that graph because there's a closed circle there. Then the graph continues forever in the positive x direction because this is going to keep going down. So my x coordinates are going to keep getting bigger and bigger. So I can say that my domain is going to be include negative 4 and then extend forever to the right, and that would be written as positive infinity. Come on back here. So this would be positive infinity. All right, my y coordinate or my range is going to be from the lowest y value up to the highest y value. Well, this graph continues forever. So my lowest y value, there isn't one, it's negative infinity, and this graph would extend up to the y value 4. So my range is going to be from negative infinity, that's with a parenthesis, up to and including 4. And that's our domain and range. And below it are some of the notes that we did that are in that function. Okay, you're given this function, and then you're told f of 2 is 7. So this is telling us that the point 2, 7 is on the graph. Find the value of a. So what you do is you plug 2, 7 in for x and y. Remember, f of x is the same as y. So I'm going to take out f of x, replace it with 7, and then each occurrence of x I'm going to replace with 2. And solve this now for the variable a. All right, our next question asks us to find the value of a. So what you'll do is you'll substitute in 2 is your x coordinate. So every place where you have an x, you're going to substitute in the value of 2. And then where you have an f of x, that's the same thing as y. So I'm going to substitute 7 in for that y value. our equation will look like this once we do the substitutions. And then we're going to work this out, collect our like terms, and then solve for A. And then once I go ahead and multiply this out, collect up my like terms, solve for A, we get A is -5. So this problem just comes down to a matter of substituting in and recognizing that this notation right here, when you see this, this is telling you an X coordinate, and this is the Y coordinate that goes with it. And then you can substitute those back into the equation so that you get an equation with only one unknown in it, and then you can solve that unknown. Okay, number 5 is asking you to evaluate, this is a composite function. So what we're doing is when we have a composite, what that means is that we're going to insert g of x into f of x. That's what a composite function does. Okay. Our notation means you are inserting the function g of x into f of x. All right, so what all that means is that when we see an x here, we're going to put in its place the expression 2 minus 3x, and then simplify it. So f of g equals square root. Now, in place of that x, I'm going to put in g. So that will become 2 minus 3x. And then I copy the rest of this, which is just going to be minus 6. And then simplify that. I have 2, and I got -3, or excuse me, this would be 2 minus 6, which would be -4. So -4 minus 3x. That is my composite. All right, now to find the domain of that. So on our domain, we have these are the only situations you've got to worry about domain. And in this example, you have a value under a square root. So this expression here has to be greater than or equal to 0. Otherwise, you can't do a square root. So to find the domain of this, we're going to take the radicand, which is -4 minus 3x, and set it greater than or equal to 0, and then solve that. So we add 4, and we end up with -3x is greater than or equal to 4. Then I'm going to divide by -3, which means I have to flip the inequality. I get x is less than or equal to 4/3. So any value that is less than, or I'm recording this, sorry. Any value that is less than 4/3 works. So that means from -infinity up to 4/3 and including 4/3 because of that equal sign, then that would serve as your domain. So on this page here, I put the other notes on domains, on how you find them, as well as some examples from the notes that we took during that time. So the one that we just did would have been similar to this example right here. Okay, for number 6, there's 3 questions. The first one, okay, G of F. So that tells us that we're going to put F into G. F into G, whatever the second function is. Okay, so our G function is 3x plus 13. Howdy. And I'm going to take out that x, and in its place, I'm going to put f of x, which is x squared minus 3. So that's going to equal 3 times x squared minus 3 plus 13. And then we just simplify that. 3x squared minus 9 plus 13, which is 3x squared minus 9 plus 13 is positive 4. And that's my composite function. All right, now to do the composite of, to then evaluate these, well, you did the composite, it's right here. So all I've got to do for this next part is substitute x into my equation that I found here. So I'm going to go 3x squared plus 4, that's my composite. And in the place of the 3, I'm going to put, or in the place of the x, I'm going to replace it with 3. So that's 3 squared plus 4. So that's 27 plus 4, which gives me 31. Right, and then on the final one, G of F negative 2, it's the same thing. I'm going to take my composite, and in the place of the x, I'm going to put negative 2. So I get 3 negative 2 squared plus 4 plus 4 plus 4 is 16. Howdy. All right. Graph a function is given the right. Use a horizontal line test and turn it into 1-to-1. So we call 1-to-1. Each element domain has only one element in the associated with it. So this would be, this is 1-to-1. Every x has exactly y. So in this context, we're using 1-to-1 to see if something has an inverse. Okay, if a function is 1-to-1, then you can graph its inverse, and its inverse will be a function. So the way that you tell if a function is 1-to-1 is you do the horizontal line test. So if the horizontal line touches this more than once, then it is not 1-to-1. So this function is not 1-to-1. Okay, this would be a many-to-1. Right? For example, let's say I pick this point. Okay, this is, I don't know, 1 3/4. Okay, so in this one, 0.5 would be associated with -4. And 1.75 also be associated with -4. So it's still a function, it's just not a one-to-one, it's a many-to-one. So as it's drawn, this curve would not have an inverse unless we restricted its domain, which is one of the next questions. So if I just say this half, if I just look at this half, okay, it's still not one-to-one. It still doesn't pass the horizontal line test. But let's say I restricted the domain. I said, what if we just look at this part of the graph between -1 and 1? Does it pass the horizontal line test? And then the answer is yes. So in order for this function to have a inverse, we have to restrict the domain between 1 and -1. Otherwise, it does not have an inverse. All right, 8A is asking us for f of 0. So that just means we're going to plug 0 in for x. There's our function f. So now I just replace the x with 0. And I get -4. Okay, now part B is the inverse of f. Okay, so what that means is you first have to get the inverse. When I see this means the inverse of f. So I'm going to take function f and I'm going to write its inverse first. Okay, so to get the inverse, replace f of x with y. So this is my original function. And now I'm going to replace f of x with y. Okay, then my next step is I'm going to change x to y and y to x. Then I'm going to solve that equation for y. So solve this for y at 4. And I get x plus 4 equals y cubed. So at this point, I either want to do the cube root or I want to raise it to the 1/3 power. Okay, either one, they're the same thing. So if I raise this to the 3rd power, or the 3rd power, I should say, and this one to the 1/3 power, these cancel, and I get y equals x plus 4 to the 1/3 power. Now I could write it like that, or I could write it as a cube root. It's the same thing. Then the last step is replace y with the inverse notation. So take out the y and I write it as f -1x. That's my inverse. Okay, so that inverse goes. Now, to answer the question, once I have the inverse, now I'm going to plug -4 in for x. Okay, so to get I'm going to put -4 in here. That's just 0. Cube root of 0 is 0. All right, now 8C, if you know what you're doing, doesn't require any work. All right, so what an inverse does. Okay, so for example, if you look at the first problem here, okay, you're told that f of 0 is negative 4. So what that means is the point 0, negative 4 is on the graph. Now the second one is f negative, the inverse of negative 4. Okay, well, all that means is that's just this reversed, negative 4, 0. So we could have done part B without doing any of this algebra. So again, let me reiterate here. If let's say 1, 2 is on f of x, then 2, 1 is on the inverse of f of x. Okay, you're just switching x and y. So if you realize that here, this is the point 0, negative 4. Well, now negative 4 is the x, so the y would have to be 0. Okay, so what an inverse does on this next problem, these two things undo each other. So if they undo each other, you're going to end up with what you started with, which is 568. So if I had, for example, if I had f of x negative 4, okay, these undo each other. So this is going to take negative 4. Here's what's going to happen. It's going to take negative 4. It's going to change it into a 0. And then it's going to go into regular f, and it's going to change it back into negative 4. So if I did it with like little machines here, okay, this is the inverse. Right? If negative 4 goes into that, out comes 0. And then that 0 goes into the next machine, which is f of x. And we know that when zeros go into the regular function, a negative 4 comes out. So you end up with what you started with. Didn't change it. That's what's happening on part C. Okay, use the table to evaluate these composite expressions. All right, find G of 3. G of f of 3. All right, so G of f. All right, so what you're going to do is first, you're going to find what's f of 3. So when I go over here, here's function f. Okay, when x is 3, out comes a 6. Now you're going to take that 6 and you're going to put it into g of x. So when x is a 6, out comes a 7. So I started over on my f. I found f of 3. My output was 6. That output became the input and g and gives me a 7. Right? Our next one is f of g of 4. So I'm going to start with g of 4. So go up here, g of 4 gives me a 6. Now that 6 is going to go into f. So f of 6 now, there's 6. That ends up giving me 3. Right? G of 6. So we start with G of 6, right? That gives us 7. Okay, and then that 7 is going to go back into G. And if you look here, there is no 7s as an input. So this is undefined. All right, it says, while a function may not be one-to-one when defined over its natural domain, it is possible to restrict the domain in such a way that it is one-to-one, and the range of the function is unchanged. Okay, so for the function f of x equals negative x squared minus 4, right? Decide on a suitable restriction of the domain so that the function is one-to-one. So what we would do is we would look at this function. So if I graph this function and took a look at it, okay, we're going to find out that when we'll do it here on our calculators in a minute, but it's going to end up looking like it's going to be a parabola opened downward, whose y-intercept is at negative 4. So it's going to look something like this when we end up graphing it. Right? So let's do that real quick. Okay, so I typed in the equation, and now we're going to go zoom and just put it on a regular graph. So that's zoom 6. And there's our graph. Okay, so that's what it looks like. All right, so this is the graph y equals negative x squared minus 4. Now, just looking at this, its natural domain would be from negative infinity to infinity, because there's no square roots, there's no variables in the denominator, there's no restrictions on this. So you can plug any x value you want and you get a y value. All right, so, but the problem is this does not have an inverse, okay? It's not invertible or non-invertible because it fails the horizontal line test. This is not a one-to-one function, all right? For example, negative 1 and 1 have the same y coordinate. If we were mapping this, 1 and negative 1 both get matched up with the same y value. So it's not one-to-one, it's many-to-one. Right? So I can't do its inverse. However, if I take the domain and I change it so that this would pass the horizontal line test. For example, if I said, instead of using this as the domain, let's say that the domain is from 0 to infinity. Okay, then this graph, this half of the graph wouldn't be there, and it would now pass the horizontal line test. Now, I could have said also, let's let the domain be from negative infinity to 0. And if we graph that, then the left half of the graph would show up, but the right half wouldn't. So this wouldn't show up. But now this part of the graph would pass the horizontal line test. So if I changed it to either one of those, the function would now have an inverse. Okay? Without changing it, this does not have an inverse. This is non-invertible. If I get rid of part of it, like if I change the domain to be from 0 to the right, it is now invertible because it would pass the horizontal line. So out of my choices here, I have from 0 to infinity would be the correct answer. All right, the graph of f is shown. Use the graph to find the inverse of 7. All right, so if we look at this graph here, this is normal f. So we got x, f of x. All right, if I, for example, look at this point, 1, 2, 3, 4, 5, 6. Okay, that's the point 6, 0. Right? So if we did the inverse, this would be 0 and it would go back to 6. All right, so we're finding f of 7, f, the inverse of 7. So what we're looking for is what value over here has an output of 7. A y value of 7. 1, 2, 3, 4, 5, 6, 7. That's this point right here. Okay, that point is 6, 7, 8. That's the point 8, 7. So when x is equal to 8, 7 is my output. So when 7 is now the input, it's the input into the inverse, 8 is going to be the output. So this would equal 8. All right, so to keep in mind, on my original graph, 8, 7 was on f of x. So that means that 7, 8 is on the inverse of f of x. When 8 is the input, 7 is the output. Now 7 is the input, and 8 is the output. Just switching them, switching x and y. All right, it says find f of g of x and g of f of x and determine whether the pair f and g are inverses. All right, they're going to be inverses if when you do these compositions, you end up with the identity function, which is x. So that's what this is saying right here. Two functions are inverses of each other if their composition results in the identity function f of x equals x. All right, so if I did the first one, my first composition, f of g of x. So I'm going to put g into f. Right, so 4. Now I'm going to put g in that x. That's x plus 4 over 2. Now we simplify it. So I get 2x plus 8 minus 2. So that's 2x plus 6 right now I know that these are not inverses because that's not just plain x. And if I do the other one now, I do g of f. So this is f into g. So I'm going to take out this x, and I'm going to put f in its place. So I get 4x plus 2 over 2. So that's 4x over 2 plus 2 over 2. And that is 2x plus 1. Okay, so these are not inverses. To be an inverse, this answer needed to be just x, and so did this one, and neither of them are. So these are not inverses. Okay, so we're going to first do f of -3, get an answer, and then we're going to put that into g. So let's see, read the graph. F is this blue one. This is f. This is g. So f of -3, 1, 2, -3, I go up, and that looks like it's the point -3, 1. So I get a 1. Now I take that 1 and I put it into g. So g is the red graph. So I'm going to go to 1 and find out what y coordinate belongs to that. So here's 1, and then I'm going to go down till I hit g, and that's the point 1, -1. So that is my solution, negative. All right, give the domain of the function below. So what I have is I have expression underneath a radical. So if I look down here, that's like this case right here. Okay, what I do is I take that expression and I'm going to solve it for x has to be greater than or equal to 0. All right, now we just did this on the last test. So what you're going to do is find what numbers make it equal to 0. So I solve this expression. So I'm going to move the 36 over, and I get negative x squared equals negative 36. Okay, divide by -1. Get x squared equals positive 36. And now take the square root. Get x equals plus or minus 6. All right, now to solve the inequality, we make a sign chart. -6 on it and 6. And I'm going to look for the intervals where I have a positive value or equal to 0. Okay, so I got 36 minus x squared. Okay, I'm going to test some numbers here. So easy numbers to test would be like -10. So if I did -36 minus -10 squared, -36 minus 100, that would be a negative. If I picked a number in between 0 and 6, or -6 and 6, like 0, well, 36 minus 0 squared, that's positive. And if I picked a number bigger than 6, like 10, I'm going to get another negative. So tested, right? I have 36 minus 10 squared, take away 100, that's negative. So the only values that I'm allowed are values that make this, or that keep this 0 or bigger. So that's going to be from -6 to 6, because that's where it's positive. And it's allowed to equal 0, so I can include the 6's. So this would be -6 to 6 with brackets, because it's allowed to be equal to 0.